contain all of the data that we have. And so this is something that Alan has never done before. And we just tried to do it to show our cards to the reviewers so that we weren't hiding anything and that all the numbers made sense. So it's something that you might want to consider when you're doing any kind of uncertainty propagation or analysis in your work. Reviewers seem to really want to know where those numbers come from. And just by giving them the code and the data, we gave them the seismic isopachs too. They can do whatever they want with it. And it'll get published as well too. So what does it mean for moving forward? Does it actually, all this mass coming off, influence the tectonics? So this is kind of where we are next. We're trying to figure out where the erosion is actually occurring. So this is the hard part. This is looking at the sediments and doing the provenance work. Where part of the mountain range is all of the mass coming from? This is results from down here is from that Pedersen and Engholm paper where they actually, these are sort of their erosion rates and sediment fluxes hypothetically over this time period. These are our data that we see here. So decreasing, ramps up, decreasing, decreasing, ramps up, as well as what we think is a way to test it by looking at where we think the erosion's occurring. And that's essentially where we are right now. Myself and my colleagues are doing all types of provenance work to isolate this down to where in the mountain range it's all occurring. We have some ideas though, and it's guided by work that glacial geologists have done. And this is Rachel Headley and Michelle Kopis and Bernard Halle, the ones that are actually working on that ice sheet model. They've done work in the area, and they actually find that the fastest ice flow is through these very narrow areas. So this is the Malaspina. This is some of the ice that's back in here. And essentially for their models, they have the erosion power here depends on basically the sliding velocity and how it's coupled to the bed as well. There's some empirical constants in here. But essentially, it's the sliding velocity. It's the ice moving through the area that removes the rock. And what you'll notice is that it's not uniform spatially. It's actually constrained to areas where there are faults, major faults. And this feeds back into Geomorphology 101, is that river systems are there because the rock is weakest there. And then if you start off with a river system, when you put ice on it, the ice is just going to follow the river system. And so you end up with a feedback. You have weak rock. You remove the weak rock, it brings more weak rock up, and it develops a feedback system that we think we actually can see in our thermochron data. So we got an idea that the erosion isn't going to be all spread out equally across the mountain range, that it's going to be in a narrow area of bedrock. And that's what we're testing for. We know what that rock is. We're just looking for it in terms of the provenance. And just to show you, I mean, the glaciers themselves, the long-standing idea has just been that it's sort of equal erosion. This is a classic figure from Steve Porter that's the Glacial Buzzsaw. The idea, if you look in North America or the Western Hemisphere, that ice sheets and topography are linked. So that red line there you see is known as the equilibrium line altitude, the ELA. So below that line you have net melting, above it you have net accretion. And so you'll notice that there is a strong correlation between topography, and this has been shown around the planet, that glaciers themselves are very effective at removing mass. But what's more important is that they remove it very focused areas. And this is a figure from our paper in 2008. It's looking at how fast the rock's coming up at millimeters per year. And it's all focused in this area that is the equilibrium line altitude. But it's also the area where the mountain is deforming the most. So we can't quite figure out, is the high rates of exhumation, the rock coming up through the mountain, because of climate, or is it because of tectonics? And that's what the drilling results will allow us to test. So where are we now? We think that we've made a pretty good case that there's more mass. The mid-Pleistocene transition was really important in terms of changing the volume of ice up here as well as influencing the amount of mass that's coming off the mountain range. But at 2.6 was another important transition that we had, was the onset of glaciation in the area. Work that the STEEP group has done onshore does show that the glacial erosion is focused in this area where the exhumation rates are the highest. So work that they've also done shows that the deformation is inboard here as well. And there's a lot of other work that they've done that shows from seismic data, and I haven't shown it here, that on the continental shelf, all of the tectonics on the shelf, the folding and the faulting, has all responded in less than 500,000 years by the major dump of sediment that you have out here. And it was the drilling that allowed us to put some constraints on it. It was interesting too because Lindsay Worthington did her PhD on this. And she'd mapped everything out with seismic reflection data, but had just really poor age control from wells. And she was out there doing the physical properties measurements for us. And so when we were coming back with ages, she'd expected at 1420, right when we hit that depth right there, that it would be about 1 million years. And when it wasn't 1 million years, and we kept drilling, and it was still less than 300,000 years, she's like, uh-oh. And then we got to the bottom, and it was still less than 1 million years. She was distraught. She thought her whole dissertation was just a mess, that she was all wrong. And we're like, no, Lindsay, you did the best you had with the data you had, and now what we found out is actually even cooler, because it shows, in fact, no, it doesn't happen over 5 million years, it happens over less than 1 million years. So that's the value of keeping an open mind about any research that you're doing, is that somebody will come along and prove you're wrong at some point. So, okay, so to tie it all together, what we think is happening here is we can go from those outboard records, we can show that the mid-Pleistocene transition did correspond to a major change in stratigraphy. Mass is coming off faster than it's going into the mountain range. We think it links pretty well with what we're seeing onshore here. And that, more importantly, that there's a major change in the North Pacific in general that dates to 2.6 million years ago, which I think a lot of folks were aware of, but it's pretty striking just to see what the transition was in terms of the deep sea sedimentation in the area. Okay, so some of the conclusions. We collected kilometers of rock, and you're welcome to go to College Station now and poke around at it if you want. What we have is really another important point here is that those erosion rates that we're seeing are high over millions of years. The figure that I showed you at the beginning from the Copus and Halle paper had really, really high rates for the modern, and then he dropped off by orders of magnitude to million-year timescales. What we've shown is no, they say that high for at least 1 million years. So this really goes against some long-standing views that those high sed rates could not be sustained for such a long time period. We also have a really great record here that shows this intensification of climate or glaciation in the northern hemisphere and its role in the mid-Pleistocene. A whole lot of words here, but basically we've got sediments that go from biogenic oozes right into ice-rafted debris and back to oozes. I mean, the ocean is incredibly dynamic in the North Pacific and the Pleistocene. That was one of the really stunning things that we saw. And we know that ice can retreat really quickly, but to do that again and again sort of fits in with that ice sheet model that I was showing you. We have, one of the nice things is lots of microfossils that we can use to identify other interstitial periods. This is one of the important things, is that we know what the Holocene's like, but we can use the same microfossils and other organic geochemistry to look at what other interstitials or interglacial periods were like. Let's see, oh, I already had that one. One of the things here is that we can show, we think, is that there's a direct link between the sedimentation we see out on the fan and Pleistocene climate. So one of the first records where we think we've nailed this down really well in the deep sea. One of the other really interesting things that I didn't get much into is 1418, which is that one site that Stoner lost the reversal on. We got 1 kilometer deep and only went back 1.2 million years. Those sed rates are phenomenally high. And within that interval, this is the deep sea. We're in 3 kilometers of water, 3.5 kilometers of water. Oop. We're finding sedimentary facies that look just like a fjord, which means that we've got a huge amount of meltwater come off that ice sheet, because the fjord facies we see, which is laminated muds, I've been studying for a long time in fjords. I'd never seen it out in the deep sea. Ellen Cowan was sailing with me, never seen it like this in the deep sea either. There have been evidence of it off in Norway. They're called plumites, but they're not really well documented around the rest of the world, and we've got hundreds and hundreds of meters of this stuff. Let's see. And then the more important thing for the story I'm getting at with the seismic data is the take-home message. If you're going to try to study something at a tectonic time scale, you got to tie it in with the seismic reflection data that's drilled and well dated. That's the key here. So there's, moving forward, if you want to think of a career, there's a lot of seismic reflection data out there that's just waiting to be drilled and dated. So write proposals, get them into the system. So this is where we are next. Just being able to show exactly how the mountain range is responding is going to require finding out where the erosion's occurring, and that's the fun part. So that's it. Thanks. Any questions?
And questions. You mentioned the reversal. In our oceanography core courses, we talked about reversal taking approximately 2,000 years. Were you able to constrain that to a more accurate number where you did have recovery? Do you recall?
Yeah, I think the challenge with that is going to be an independent age control throughout that reversal. And we might, I don't know, that's going to be a tough one because the uncertainty, if we're lucky, we've got ashes around there, but even there, we don't have anything in there that we could do cyclostratigraphy on, so I don't think.
And how about this microplate? You said it was composed primarily of basalt. I mean, is this an ophiolite? It's been a sliver of oceanic seafloor that's been
No, actually, it's kind of interesting. It's the Siletz terrain, if anybody's have heard of it. It's part of the same hotspot that the Yellowstone's part of. So when it was forming, you had a flood basalt kind of thing. The Columbia River flood basalts are part of it as well, too. So when it was further off, it's a lip, a large igneous province, that then collided with North America, and then part of it got shunted up north. There's another, Al?
What's the sea level story about? You mentioned it at all.
It's going up and down.
What's going up and down? It's delivering sediments, it's not delivering sediments, it's sequestering sediments.
There's a reason why I didn't mention it, because we really don't have a good handle on the ice volume over time. So we can't correct for glacial-isostatic effects. We do know that the ice is loading the crust because we've got really good evidence from the deglacial of rebound through that area. When you're at a glacial maximum, relative sea level is probably close to where it is now, maybe.
What's the sort of, I mean, you have this seismic stratigraphy there.
Yeah.
Can you see sea level events in that? Are those various reflectors indicating high stands, low stands?
It's really hard to separate out the glacial seismic facies from your traditional transgressive, high stand, regressive facies. You can use that same terminology, but to link it to an actual eustatic or relative sea level control is really hard. Because glaciers will, it's in there. And there's a story that I didn't mention either that came out of Lindsay's work, which was really amazing, is that there's the development of the continental shelf in, and it's a sea level record that's in here too. Well, basically, this continental shelf here, this transect that we drilled, like I said, sed rates are really high. It's only formed probably over the last 500,000 years. And what it had to do, though, is it's a deep part because it's where the plate's subducting. So it was deep to begin with and had to fill in the hole. Temperate glaciers will only advance as far as their terminus will allow them. They have to be anchored to the seabed. They're not like Antarctic ice sheets. So if they go into too deep a water, they begin to calve back, and they fail. So a glacier can't go out into this deep foredeep on the shelf, and it has to fill it in gradually through time. And so we see in this record, actually, is the shelf being built. And it happens really fast. But it's an autogenic behavior in the system. It has to fill in this before it can actually make it out to the shelf.
In 100K, in the eccentricity,
Yeah.
700,000 years, there have been, 4 major sea level events.
Yeah. What we see them as stadials and interstadials in our record. I mean, that's our green interstadials are there, and we've got our major glacial events. Trying to tease out the sea level record is really hard in this case because the sediment's being delivered when the ice is at the shelf edge, or is it being delivered because sea level's dropped and it's loud? We don't want to go down that road. I've done work in New Zealand. I can show you the effect of sea level there, but that's a different story.
Last question, you see any glacial bursts, evidence of glacial bursts?
Yeah. Yeah, and in fact, Mo Davies was the first to look at that in her oxygen isotopic record from one of the cores. She sees a real freshening event, and we've seen evidence for a few more things, and just in the lithofacies that might be. There's some large lakes that form back inshore a little bit that they fail as eucalypts. And we've got records of that in the Holocene too. So that's another behavior.
So they're lake generated, not volcanic generated.
Oh, I mean, in this particular area, probably not related to volcanoes. I mean, earthquakes, obviously. I mean, you had a magnitude 9 earthquake there 50 years ago, so that also plays a role in this too. either. Yep.
We've all seen that picture of Obama standing in front of that glacier.
They have been there many times, that glacier.
Yeah. And I've also seen pictures that say that thing was retreated way back, you know, in the 1800s. And it seems compatible with what you're showing here. These things go back and forth.
Oh yeah, yeah. I mean, and that's the thing too, that you know, our observations of change of ice volume, I look at it over long time scales. I can tell you though that the exit glacier that he was at when I first started working there was way down valley, and it's retreated back a lot, as all the glaciers are in Alaska, except for the Hubbard is the only one that's advancing.
It's being publicized as climate change.
It is. We're losing volume of mass up there. There's no doubt about that. And so, I mean, that's done. You can do it through flying elevation. You can do it through gravity measurements. We've lost it. It's a substantial contribution. It's not the major contribution to sea level rise, but it's part of it. Yeah, and to be quite honest, it is following the Little Ice Age, which was the major advance of ice in that area. And so what you see basically is the Little Ice Age ice retreating beginning in the late 1800s. And it actually re-advances a lot through the early part of the 20th century. And then now, since about the 80s, it's just all negative. And so it's pretty much at this point going in one direction.
After watching the Republican debates last night, I was wondering if you're concerned about not being able to use the words climate change in the future.
Well,
Our governor is...
yeah, I know. Oh, I don't have any problem with using climate change or sea level rise or any of those kinds of things. I mean, it's an interesting perspective when, you know, I'm looking at a sediment core that goes back millions of years, and I can see how dynamic the planet is over those time scales. And there was a really good thing in Slate, this is the last thing I'll say about what are courses you should take as an undergraduate. One of them is geology, because it gives you a time scale of what the planet's history is really like. And it was written by an English major. Said she learned so much about just the planet. So, yeah, it gives us a little bit of perspective that way. Yep.
These cores that you're looking at, you're seeing these sedimentation that be 500 kilometers away, and inferring, you know, the input from the coast, long ways. And I was thinking sort of like when you're talking about the river, things can happen and then the river can move.
Yeah.
To get that far offshore, I'm wondering if you had a uniform kind of input everywhere, where you're going to see the deposition is going to depend on the circulation, the ocean circulation, and the climate is going to change the ocean load.
Oh, yeah, yeah, yeah.
I'm just wondering, could that affect some of these interpretations?
Oh, for sure, yeah. For the large landslide deposits, not so much, because those are hyperpycnal flows, so those are moving down to... Oh, yeah, no, and in fact, that's why we really want to be careful about when I show a record like this, because it's one spot. And in particular, the productivity at this area is really a challenging one, because the Gulf of Alaska is a really oligotrophic water mass. But it's along the edge where you get the iron coming in. And so you can look in satellite photographs of productivity that you get these little wisps that come out right over our core site, and then they go away. And so you're right. There's got to be and ice-rafted debris, too, because it gets caught up in the coastal current. Yeah.
You see the same thing at Site 888.
Yeah.
At Pump 6.
Okay, yeah, yeah.
So,
Yeah, and then...
Gerald Howe stuff.
Yeah, right, yeah. Yeah, so there's some large-scale regional, you know, you've got a secular trend in your data, but the high-frequency wiggles, I think, in this case, certainly are probably related to changes just in the oceanography, and that's a major part of it. Yeah.
Could you run this experiment in a non-glacial environment, let's say a tropical high rainfall environment? Never has any ice, but a lot of topography.
Yeah.
Volcanoes or whatever. And so you have, you know, periods of severe weathering and then periods of non-severe weathering. I mean, there's a climate signal, but it's not an ice dominant signal.
Yeah, I think if you can, the key here is you got to be able to use seismic volumes. You got to be able to say, all of this rock that I've got here in the deep sea came from that one spot. And we've been lucky in the Gulf of Alaska because we can really separate out what's coming from the different areas. If you could do it in a tropical area, then yeah, I mean that's you could do it if you can drill it. You know, the oil companies have the drill core that you know, I mean they drill in Indonesian waters all the time. So, yeah, it's getting a hold of them. That's the key there. So it'd be a fun one to do. We want to test this next in Greenland. That's the long-term 10-year goal.
Start writing a proposal now.
I don't have to do it. Stoner's doing it.
So you've done-
Yeah, it's already done. Just waiting for the
It was a
ship
little
to.
bit too big the first time it got submitted.
Yeah, I know.
Okay, well, let's thank John, that was great.
Mhm.